This video summarizes the kinetic theory of gas, in particular ideal gas. And this is not a full description, but just a summarize. Okay, and first of all, you start from here, and then you have the model for a gas, ideal gas. Yeah, model like this. So you think about it, and molecules, hard little balls inside the box. There were trillions of them. So then focus on the pressure. Think about it. And the pressure on the system, on the wall, is basically because of the collision due to these balls on the wall. And of course, there are millions of them. And now they think about it. If they are moving at the same speed, right? And then if you have a bigger volume, with the volume bigger, and they have bigger area, and then they're less likely to hit on the walls, right? Because per unit area. So therefore, the bigger the volume, the smaller the pressure, right? Then, so if you have a pressure times the V, if you divided the V to the other side, so pressure relation with V is an inverse relation. Okay? The bigger the volume, the less the pressure. So then that gave some intuition for this equation. If you divide the V to the other side, the larger V and then smaller pressure, because simply less likely to hit the wall. Now, so therefore, normally you multiply the V to the other side, V times V, but equals the constant. Now, what if the temperature is not constant? Now, recall that we talk about temperature is nothing but the kinetic energy average. So, pressure is dependent on the temperature, because kinetic energy. Why? Because, think about it. It's kinetic energy, once again, a hitting on the wall. Think about the temperature is how fast this ball moves. With low temperature, we'll have lower speed and therefore lower V square, mv square, and lower kinetic energy. When it hit on the wall, the impulse theorem, and the force will be less. Okay, and if you faster the molecule move with higher temperature, therefore the pressure will be higher. So then look at here our gas equation. So everything is fixed just between pressure and temperature. Obviously, temperature is higher, the things move faster, the pressure will be higher. So that's intuitively fit our idea. So that's this model. All right. And then in another equation, there is another factor, and N, that is the molar number. How many of these particles in the box? So everything else is fixed. So everything else, temperature is fixed, everything is fixed, volume is fixed. Now, so then look at this again. So if you have 4, say, balls, there is more balls hit on the wall with the same temperature, there will be more. So therefore, it really depends on the number of molecules inside of the ball. Therefore, you look at this, if everything is fixed, if the number of moles goes up, then pressure will go up. So think about the rest is constant. So then, of course, this whole thing is multivariable, which means several variables tied in this equation. This is called the ideal gas law, PV equal nRT. So, and then, of course, this is how qualitatively to understand this equation. This equation is derived, in fact, from this website. It exactly derived this equation from microscopic using statistical physics, and derive it's a result of derived. It's the exact equation for the ideal gas. But now here we understand why that's the result. Okay, and actual derivation of this equation is beyond the course, but even here, we without going to mathematical detail, can appreciate this equation as it works, its validity. And now, what is this constant? Well, there is a proportion, and there is a constant. This constant is called the ideal constant, but that constant is the value is known. It's called a gas constant, so that's always there. So why we want ideal gas, but while the real gas like air, oxygen, hydrogen gas is not ideal, but in normal cases it's pretty close to ideal. So you can solve many problems with this equation. All right. So, but just at a normal temperature, it's very close to this equation. So therefore, this is very useful. And of course, at a low temperature, extremely high temperature, high density, and this equation will break down for some real gases. But in normal cases, this is pretty helpful. At least you know the trend. Okay, and from this equation, you can derive some other known good thing you take home with is this number. Okay, because to the model you only see 3. Okay, you only see 3, but actually that's just simulation. There's trillions of them, and that's in there. So then, therefore, this mole number is how many moles. Each mole of gas has a lot of molecules, but it's a fixed number. This number is 6.03 times 10 to the 23 moles of molecules. So, which means if you have, say, 1 mole of hydrogen gas, how many of them are there? This is the number. Okay, this is the number. And then, so then 1 mole of anything is this many number. Of course, once, because the molecule could be big, could be small, but it doesn't matter. But anything we count by numbers. Okay, is this much number. Therefore, 1 mole of something, different gases may weigh differently, have different mass, simply because the molecules are bigger or smaller. So then something, if you from this equation you can calculate 1 mole of hydrogen, 1 mole of gas, and in standard pressure is this much volume. Okay, 1 mole of is any gas. Okay, that's cool. It's any gas, almost. And under standard pressure is 22.4 liter. Now 24, you know how big is a liter? It's like a tissue box. 24 liter, 24.4 liter, any gas. So, and how can you get this result from this ideal gas equation? Use a standard temperature is about 275 at 0 degree, almost ice point, and that's a constant. And you have 1 mole, put a 1 here, and 1 cubic meter, and then standard pressure is atmospheric pressure. And then you can have, you solve for V, you get 22.4 liter. So standard pressure, 1 mole, gas constant, ice point, absolute temperature, you solve how much is the volume, and you get 24. And that's a good number to remember. And 1 mole of anything. So 1 mole, for example, 1 gram of hydrogen gas, at standard condition, we'll take how much volume is it? And 24. So 1 mole of water vapor and steam at at this temperature and 0 point will weigh the same volume. Okay, 1 mole of oxygen gas at standard pressure, standard temperature is 22.4. Any gas will have this volume. But the condition is that standard atmospheric pressure is like 1.3 kilopascal, and temperature is 0 degrees Celsius, and which is so at this volume. So that's common. But in any other volume, any other temperatures, all have this equation. So you will have some problem to solve with this. We will have exercise with this equation. So far for the video. So PV equals nRT. So you will solve this problem with this equation.